So now that we have understood the case involving two risky assets and one risk-free asset, we can generalize it to n risky assets and one risk-free asset. And in fact, this is indeed what the Markowitz model that we saw last week actually does. So the Markowitz model has basically the three parts in terms of the optimization problem. The first step involves identifying the risk-return combinations available from the set of risky assets. The second part involves identifying the optimal portfolio of risky assets by finding the portfolio weights that result in the steepest capital allocation line. And finally, it involves choosing an appropriate complete portfolio by mixing the risk-free asset with the optimal risky portfolio. So before we get into a bit more detail, notice that these three parts that we have just mentioned, they are exactly the steps that we had followed when we were discussing what happens if you have got two risky assets and one risk-free asset. So I encourage you to pause the video at this time and just think about the analogy for each of these three steps in comparison to what we just saw before. Okay, so let's look into a bit more details. So in the first part of the problem, which is basically the risk return analysis, what we do is that we want to have n different risky assets, okay? And we want to focus on this to come up with the set of options that are available that can be created from this n risky assets only, right? So what is needed as an input is basically an estimate for the expected returns of these n risky assets, okay, as well as a set of estimates for the covariance matrix. Now, what do we mean by the covariance matrix? So this is the matrix which contains the variances of each of these n risky assets. So we require information about n of these variances. And we also require information about the covariance between the different risky assets, right? So how many such covariances do we need? Well, basically, you have got the covariance matrix will have n cross n. So total entry will be n square. Out of the n square entries, n of them are the diagonal entries, which would correspond to the variance, right? So we can eliminate those. So n square minus n. And again, you have got covariance between I and j is the same as covariance between j and I. So basically, we just need the half of that, right? So n square minus n by 2. So that's the total number of covariances that we need at our disposal. Okay. So once we have these estimates of the expected returns, variances, and covariances of these risky assets, then we can get on with the identifying the possible combinations that are possible. So we will need the expected return for the different weights that we have in mind. And we would also need the variance of the portfolio for the difference weights that we have in mind. So these are standard formulas that we have discussed now multiple times. So expected return can be calculated as by the weighted average of the expected return of the underlying assets that we are considering. And the variance can also be calculated using this formula that we have seen before. Okay, so what this is doing is that it helps us to identify the efficient set of portfolios, right? Or the efficient frontier. So we are not just interested in understanding what are the possible combinations. We also want to think about what are the efficient combinations among those possible combinations, right? So the main idea is very simple. Either we kind of fix the risk level that we are interested in and think about the portfolio which will give us the highest expected return constrained to that risk level. Or alternatively, we can think of fixing the targeted expected return and then think about the portfolio that will give us the minimum variance corresponding to that, right? And here you might also want to incorporate in other additional constraints, such as perhaps if short selling of certain assets are not permitted, or there are some socially responsible investing that requirements that are there and so on, right? So let me actually illustrate these points through a diagram that you have seen before, and then let me come back to exactly what are the implications of this. So this is something that we had seen before. So you have got in different individual assets, right? Out of which we can create the minimum variance frontier, which is this curve as a whole, right? Both the upward portion and the downward portion, right? Why is this minimum variance frontier? Because this is telling us, for instance, for the given level of expected return, right, which portfolio can be formed that has the lowest variance, right? So there may be these other portfolios that are available to us here among these points as well. However, this frontier actually is telling us that what is the lowest variance one corresponding to each of these things, right? So you have all these points that are here. Among them, the one with the lowest variance is what is known as the global minimum variance portfolio, right? And finally, we had discussed that the upper part of this curve is an efficient frontier. Why is that the case? Because suppose that you fix a level of sigma, right? Then there are 2 points on this minimum variance frontier that would be actually in line with this. However, only one is going to give a strictly higher return compared to the other one, right? And so therefore, that is the only point that should be on the efficient frontier, right? I think this graph actually makes these things clear. So if we fix, for example, expected return of R3, this is the point which would be on the minimum variance frontier. And similarly, if you fix expected return of R2, this is the point that is on the minimum variance frontier and so on, right? But suppose now that you want to fix sigma A, so there would be potentially 2 points, right? One here and one here. But we would want the one which is on the upper part of this curve, right? Because that gives a higher expected return compared to the one which is on the lower part with the same value of sigma A, right? So that's why the efficient frontier of risky assets would only have the higher portion, right? So this is, I hope that this makes clear these 2 bullet points. And finally, what do we mean by the last one? So there can be like additional constraints, right? So remember, when we draw this picture, perhaps we have not incorporated in the fact that you can actually not short some assets, right? So if you have those additional constraints, then possibly all these points will not be achievable, right? So some of the weights that we considered may have actually had a negative weight, right? Which is the part that comes from shorting some other things. So if that is not allowed, then in that case, this will not necessarily be the set of all points that are achievable, right? Similarly, socially responsible investing might involve saying that there's only a certain amount that you can invest in a particular industry, or perhaps you cannot invest at all, right? So then again, that would reduce the set of visible points that are available to us and therefore would affect the efficient frontier, right? So that's the idea. So if you have such constraints, this is the place to incorporate it in the optimization exercise. Okay, so that was the first part. What about the second part? So once you have got the efficient frontier, the second part actually starts about how do you incorporate in the risk-free asset, right? And this is very similar to what we have discussed before. So imagine that point F here corresponds to the risk-free asset, right? And what you want is now among all points that are on the efficient frontier, you want to think about which point do you want to combine with the risk-free asset, right? And as we have seen before, so suppose you have a choice between combining portfolio G with F or portfolio A with F, you would typically prefer to have portfolio A, right? Why is that the case? Because that will give a line with a steeper capital allocation line, right? And therefore, for the same level of sigma, you can achieve a higher level of expected return if you combine F with A versus if you combine F with G, right? And we can again go to the extreme case and think about, okay, which one is the best among all these points in this efficient frontier? And again, the answer comes around from a tangency argument. So the point P, which is the tangency portfolio, is actually the optimal risky portfolio from the manager's plans, right? In the sense that it gives the one with the highest slope of the capital allocation, right? Okay. And that also corresponds to the highest Sharpe ratio as before. So one thing to note is that one implication from this is that the manager will actually offer the same risky portfolio to all clients regardless of their degree of risk aversion, right? So again, this portfolio P is constructed from combining the different risky assets, right? And this is the portfolio that we want to combine with the risk-free asset, right? So this same option, P, is going to be made available by the portfolio manager to all of the clients, right? So why is that the case? Because basically, once you are faced with these two options, the risk-free asset and the risky portfolio P, then depending on the risk aversion that you have, you can decide how much of your money to invest in P versus how much to invest in the risk-free asset, right? So that part is where the risk aversion will come in. But to all customers, regardless of the risk aversion, the same portfolio P is going to be there, right? So this is the interesting part in part two, which is that you get that everybody is going to, depending on regardless of their risk aversion, everybody should end up using this same portfolio P as the optimal risky portfolio, right? Okay, so this result is actually a separation property, right? What it means is that you can actually separate out this optimization problem into two parts. One is that in the first part, we just focus on just the kind of like the risk profiles that are available for the different assets, right? So the estimates that we have seen before, and on the basis of that, come up with the optimal tangency portfolio, right? In the sense that we have talked about. And in this part, you do not need to consider the risk aversion part, right? And only in the second part, when you have finalized what's the optimal risky portfolio, and you know what the risk-free asset is, and you are thinking about how to divide up your money, that's when the risk aversion of the investor actually needs to factor in, right? So this is actually a very interesting result, and it's in fact the theoretical basis of the mutual fund industry, right? Which says that you have got the amount of money that you want to invest is up to you, but typically you should agree that this is the best thing that you can do in terms of if you want to invest in a risky asset, right? So one interesting question is that then why do we have different risky portfolios for investment, right? Because the Markowitz model says that everybody should have the same risky asset to invest in, right? It's just that you invest a different fraction in the risk-free asset versus the risky asset, but the risky portfolio should all be the same for everyone, right? So there are several reasons behind that that we have not considered. So one of them can potentially be that different people have different beliefs about this estimates of the underlying securities that we have seen. If somebody's estimate of the expected return or the variances and covariances are different from mine, then we would come up with different measures of what should be the optimal risky portfolio, right? And so therefore, it would not be the same portfolio that is being offered. There are other reasons as well, based on different constraints that different investors might face, such as whether you can actually short some assets or not, as well as whether you have different tax implications depending on the amount of money that you have and so on. So then if you factor in those different things, then it's possible that there might be different optimal risky portfolios for different investors. But in the absence of such frictions, the result is quite strong, which says that should be the same optimal risky portfolio for all the investors, regardless of the risk aversion. The only difference is going to come in from the fact that different investors having different risk profiles would be putting different weightage on this optimal risky portfolio in their complete portfolio, right? So that's the end result. Okay, the third part of the problem is actually quite same as what we have studied before. So instead of getting into more details into that, let us look at a particular example to see how these things play out. So in this figure, we have got three different assets, right? So these orange dots represent the three underlying risky assets, right? And there's also a risk-free asset, which is giving a return of 2%, right? So the first question is, how do you come up with the Sharpe ratio for any any particular combinations. So the point which is represented by this blue dot here is actually achieved by combining these three different risky assets in different proportions, right? So the proportions are actually listed here. So the weight of the risky asset one is 50%, weight of the risky asset two, which is this one, is 0%, and weight of the risky asset three is therefore again 50%. So that's how we got the blue dot, right? And we can now calculate the Sharpe ratio of this blue dot by looking at the point which connects the blue dot with this risk-free rate, and then looking at the slope of this line, right? The blue line that we have here, right? So that's how you can calculate the slope of this, the Sharpe ratio, right, of this portfolio. Okay. The next thing is that, okay, how do we then calculate the tangency portfolio? So again, these are the three different assets, okay, which are represented here. This is the risk-free rate, and we can draw basically the minimum variance frontier and therefore the efficient frontier in a way that we have discussed before, right? And then the Sharpe ratio is basically kind of like just looking at the slope, as again we discussed. So the tangency portfolio is going to be the one which gives the highest value of the Sharpe ratio among the points on the efficient frontier, right? And so therefore this is the one that we have, right? So the interesting thing, as we discussed, is that doesn't matter what the risk aversion is, it's going to be the same tangency portfolio that is actually going to be used to optimize. And we are going to see an illustration of that here. So first, this is our benchmark case that we have built these different kind of like assets, and then from that we have got the tangency portfolio from which we have identified this point, right? And now suppose that you have got mean variance preferences, which is our usual one, expected return minus half A times the variance. And suppose the value of A is first, we set it to 6, right? Then we'll find that this is our usual indifference curve, and then the optimal point is given by this star. Okay, so somewhere between, we can see between 5% and 10%. So the idea is you're going to be kind of like, this is the standard deviation. So you're going to be investing some of your money in the risk-free asset, which gives 2%, and some of your money in this tangency portfolios, which is our optimal risky portfolio, and you are going to end up on a point which is this star, right? This is where the indifference curve is tangent to the capital allocation line, which is formed by joining the risk-free rate and the optimal risky portfolio, right? So what it says is that you're going to invest some of the money in the risk-free rate and risk-free asset, and some of the money in the optimal risky portfolio. And as a result of that, this is the combination of the expected return and standard deviation that you are going to achieve at your optimal point. Okay. Now the question is, suppose that we change the risk aversion, right? How will this picture look like, right? So this is for risk aversion 6. And now if you look at this for risk aversion 8, we can basically see that you have basically just moved along the same straight line, right? So this is the same straight line which connects the risk-free asset, right? So the 2% that you have was with the same portfolio, the tangency portfolio that you see in the two pictures, right? The only thing that has changed is that the optimal point has basically shifted a bit to the left, right? So this makes sense, right? This is basically saying that if you're more risk averse, you are going to probably choose at an optimal point something which has a lower value of expected return, but more importantly, has a lower value of standard deviation, right? So this is basically, you have just moved along this line to the left, right? The tangency optimal point is happening to the left. And as you would expect that instead, if we are just reduce the risk aversion, right, then we see that again, it's the same line along which you are moving, but now the optimal point is going to be much to the right, right, where you are wanting a higher value of expected return, even if it is coming at a higher value of standard deviation, right? So the important thing is it's the same capital allocation line, the one that connects the optimal uh, risky portfolio with the risk-free rate along which you are moving. And it basically means that different people are just putting the money in the same portfolios. It's just that they are putting different weights on this risk-free rate versus on this risk-free asset versus this optimal risky portfolio that we have formed before, right? So that's the implication. And these are, by the way, generated by this same set of interactive tools that we saw before last week. So you are also free to go to this Rice Business School website where they have this nice interactive things for one to kind of play around with. And you can just change the different values of risk aversion, risk-free rates, the different characteristics of the portfolio. So their expected returns, covariances, variances, and so on, and see what happens. And they also give the Python code. So in case you are interested in kind of like seeing how these things are generated, also that is an option that is also available to you.